Good morning, welcome to new lecture. Today I will review several examples about slope deflection method. First problem, we have this beam. So ABC 20 feet, 30 feet, and we have distributed load, uniform distributed load here for entire beam. So entire beam is subjected to uniform distributed load, and the intensity of the load, it is 2 kips per feet. We want for these two spans beam find reactions. Okay, this is a very easy problem. First step, we will find fixed end moment, and fix AB will be equal to WL squared over 12. That will be equal to 2 times 20 squared over 12. That will be 66.67 feet kips. And fix BA will be equal to negative WL squared over 12. This is counterclockwise, positive, and other one clockwise, it is negative. That will be again equal to negative 2 times 20 squared over 12. That will be negative 66.67 feet kips. M fix BC will be equal to, for this span again, WL squared over 12, that will be equal to 2 times 30 squared over 12, that will be equal to plus 150 feet kips. And M fix CB, magnitude will be the same, but the direction will be in inverse direction, negative 150 feet kips. So we found all fixed end moment. Then I will write slope deflection relation. MAB will be M fix AB plus 2EI over L 2 theta A plus theta B, because there is no settlement or lateral displacement. That side term, it is 0. I don't write that one. This will be equal to 66.67 plus 4EI divided by 20 theta A plus 2EI divided by 20 theta B. MBA will be equal to negative 66.67 plus 2EI over L20. That will be 2 theta B plus theta A. MBC will be M fix BC 150 plus 2EI over L, here it is 30, the BC span, times 2 theta B plus theta C, and MCB will be equal to M fix CB, negative 150 plus 2EI over L 30 times 2 theta C plus theta B. These are slope deflections equations. I wrote all slope deflection equations, and let's look at to see how many degree of freedom this system has. we have 3 nodes and all of them they can rotate. So we have 3 degree of freedom. Degree of freedom it is 3, and they are theta A, theta B, and theta C. These are our unknowns. So we have 3 degree of freedoms, and if we solve using the slope deflection, we will have 3 unknowns. Our 3 unknowns, it is theta A, theta B, theta C. What are the equations? Let's write equilibrium equations. Equations, one of them we know, MAB is equal to 0. This is one equation. Another equation, because this is rigid joint, this is continuous, we know MBA plus MBC should be equal to 0. This is second equation. Third equation, MCB, again because it is hinge, it is 0. This is 3. 3 equations, 3 unknowns you can find. So, MAB, MBA plus MBC, MCB. From slope deflection equations, we will plug those here. So we can find EI theta A is equal to negative 83.33. EI theta B will be equal to negative 500. EI theta C will be equal to positive 1375. So from those slope deflection equations I wrote, I will plug here. We will have 3 equations in terms of theta A, theta B, theta C, and we have 3 equations, 3 unknown. We will find those 3 unknowns. After finding these 3 unknowns, we know now theta A, theta B, theta C. We will plug back in the slope deflection equation. So we can find moment AB, BA, BC, CB. If you plug those theta in slope deflection equations, you will find MAB is equal to 0, MBA is equal to negative 175, MBC will be positive 175, and MCB will be equal to 0. Okay, let's look at to the next example. Next example again, we have this beam. feet, 30 feet. It is subjected to uniform distributed load. The intensity of the load, it is 2 kips per feet. I for here, it is 900 inch to the power of 4 for BC part. A, B, C. I for AB part, it is different, 1200 inch to the power of 4. So we have this beam. This beam is subjected to uniform distributed load. The intensity of load, it is 2 kips per feet. And AB span, it is 30 feet. BC span, it is 20 feet. I for AB part, it is 1200 inch to the power of 4. For BC part, it is 900 inch to the power of 4. And E, it is equal to 30,000 KSI. We want to find reactions. Again, first step, we will find the fixed end moment. Fixed end moment for all of them, the formula, because it is distributed load, uniform distributed load, it is WL square over 12. If counterclockwise, positive, clockwise, negative. So for AB will be 150 feet cubes. For BA will be negative 150 feet cubes. For BC it is equal to 66.67. For CB will be equal to negative 66.67 feet cubes. Now I will write again slope deflection equations, and for all of them the formula is similar to previous example. For example, MAB is equal to M fix AB plus 2EI for AB part divided by length of AB part 2 theta A plus theta B. You can write similar equation for BA, BC, CB. So you will have equation, slope deflection equation for MAB, MBA, MBC, MCB. Pay attention, in each part put right length for the span. If it is AB and BA, it should be length 30, and if it is for BC and CB, length should be 20 feet. And again, pay attention to the I, because I is different for AB and BA. I will be 1200, for BC and CB it will be 900. And again, pay attention to the unit. This is feet, this is inch, so you should be consistent. After writing those slope deflections equations, you will look at the condition here you have. Theta A, it is fixed support. We know from beginning it is 0. So instead of theta A, we will plug 0. How many degree of freedom we have here? We have 2 degree of freedom, 1, 2. Because this can rotate, this can rotate. So our unknowns are theta B and theta C. So you will need 2 equilibrium equations. One of them will be MBA plus MBC is equal to 0. Because this is continuous beam, MBA plus MBC should be equal to the 0, because that joint should be in equilibrium. Another one, MCB, should be equal to the 0, because this is hinge and moment at the hinge is always is equal to 0. So 2 equations you will plug in terms of slope deflection equations. 2 unknowns, theta B and theta C, you will find. After finding theta B and theta C, you will plug in the slope deflection equations, so you will find moments. If you follow all steps right, MAB will be equal to 163.55, MBA will be equal to negative 122.86, MBC will be equal to 122.86, and MCB will be equal to 0. So I didn't write details because it is easy and you are able to do it. I am sure about that. Let's look at the frame example. All of these examples I solve, they are beam. Let's see if we have a frame. Even that frame, it is sway frame. It can deform laterally. We have side sway deformation. In that case, how we can solve that frame using the slope deflection equation? Everything is the same, a little bit maybe more detail. Let's solve one example. I have this frame. This column is subjected to distributed load, uniform distributed load, and the intensity is 0.5 kips per feet. So this column is subjected to uniform distributed load and the intensity is 0.5 kips per feet. We have one concentrated load here, that is 40 kips. And from here to here it is 12 feet. From here to here it is 8 feet. So entire this span it is 20 feet. And the height for this frame it is 16 feet. We want to find moment at joint and lateral deflection or deformation for this frame. Let's put name for joint A, B, C, D. And the I for this column it is 3I. For this column it is 2I. And for this beam it is 5I. Even moment of inertia it is not uniform, and in reality usually it is not uniform. So this is 3I, 5I and 2I. Let's see how we can solve this using slope deflection. First step again, we should find fixed end moment. Fixed end moment for AB, again it is distributed load, WL square over 12. It will be 0.5 times 16 squared over 12. That will be 10.67 feet kips. M fix BA, because it is uniform distributed load, it will be equal to the AB, only it will be in inverse direction, so it will be negative 10.67 feet kips. M fixed BC will be equal to P A B squared over L squared. That will be equal to P, it is 40 here, A it is 8, B is 12 squared, entire length it is 20 squared. That will be 115.2 feet kips. M fixed CB will be negative P A squared B L squared. That will be equal to negative 40 times 8 squared times 12 divided by 20 squared. That will be equal to negative 76.8 feet kips. This frame will deform laterally because stiffness it is non-uniform. You see 3I, 5I, 2I. On the other hand, even the load, external load, it is not symmetrical. So the stiffness distribution it is not symmetrical. The load is not symmetrical. So definitely it is sway frame. And how many degree of freedom we have here? We have one rotation at A, one rotation at D, one rotation at B, one rotation at C. So we have 4 rotation, 4 degree of freedom we have there. If we convert all these nodes to the hinge, this will be unstable frame. I drew here. This will be unstable frame. It can collapse. In order, you see, it can move like this and collapse. In order to keep it in equilibrium, I need one member add here. If I add one member, this will not collapse. It is stable now. So, one translational degree of freedom, 4 rotational. 5 degree of freedom we have here. So in order to solve this frame using the slope deflection method, we need to solve 5 equations, 5 unknown system. So our unknowns it is theta. Our unknowns will be, if I list it, it will be theta A, theta B, theta C, theta D, and delta. If roughly I drove the deformation for this frame, it will be something like this. For example, joint B will move here and it will rotate. So something like this. If I show even, let's see, using red color, it will be something like this. Roughly. Something like this. So we have lateral deflection delta as well. So here our slope deflection equations, we should write complete equation. After calculating this fixed end moment, the slope deflection equations, for example for AB I'm writing, MAB will be equal to M fix AB plus 2E I for that part, it is 3I, divided by length 16, 2 theta A plus theta B plus, it is in the formula it is negative 3 psi. Psi here it is negative delta over L, so if I plug it will be plus 3 delta over 16. MBA will be equal to negative 10.67 plus 2EI, 2E times I, 3I over 16, 2 theta B plus theta A, again plus 3 delta over 16. MBC. MBC will not have that side term because the point B and C, they will not deform in lateral direction respect to each other. They will remain in the same elevation. So MBC will be M fixed BC 115.2 plus 2E. I for that it is 5I divided by length it is 20, 2 theta B plus theta C. M CB will be M fixed CB, it is negative 76.8 plus 2E I 5I, L is 22. Theta C plus theta B. So I wrote MAB, MBA, MBC, MCB for AB and BA because A and B will not remain in the same elevation. So BC, after deformation it is in the same elevation, but A and B, they will be not in the same line. For example, B will move in lateral direction, delta. So for this column, I will have that side term. So if I write those here, M, C, D will be, because here we don't have external load, M fixes 0 plus 4E, I for that it is 2I, L 16, 2 theta C plus theta D plus 3 delta over 16. And finally M DC, M fixed DC it is 0 plus 4E times 2I over 16, 2 theta D plus theta C minus 3 side will be positive 3 delta over 16. So how many slope deflection formula I wrote it, M, AB, BA, BC, CB, CD, DC. Now, let's look at the equilibrium equations. As I mentioned, here I have 5 unknowns, theta A, theta B, theta C, theta D, and delta. So in order to find 5 unknowns, I need 5 equations. Let's look at the equilibrium equation. Equations here, first equation, we know M, AB is equal to 0 because it is hinge support. MBA plus MBC is equal to 0 because this is rigid joint, and moment in both sides they should be equal in opposite direction. So if we add, they should be equal to 0. MCB plus MCD is equal to 0 because this is again rigid joint. MDC should be equal to 0 because it is hinge. Up to now I have 5 equations. I need one more. Up to now I have 4 equations. 1, 2, 3, 4. But I have 5 unknowns. 1, 2, 3, 4, 5. I need one more equation. That equation comes from the shear equilibrium. Look at here. If the shear force at point A or the support traction at point A, I show with VAD, AB, and if I show this with VDC, equilibrium equation in horizontal direction, it gives us VAB plus VDC should be equal to, summation of force in horizontal direction is equal to 0. VAB plus VDC should be equal to half times 16. That will be half times 16. But how we can find relation between these V and M? Because all theta it is, all M's it is in terms of theta. I should bring V in terms of M. So in that case our V, the shear force, will be in terms of theta as well. Look at the free body diagram for column AB. Column AB, here if I have VAB, in this side I have VBA. Here if I have MAB, here in this side I will have MBA, and here I have distributed load, intensity half, the length is 16. If I take moment respect to the point B, what I have? I will have VB times 16 minus, let's see. This is counterclockwise. I can write MAB plus MBA minus VAB times 16. MAB counterclockwise plus MBA counterclockwise minus VAB times 16 clockwise, so negative, plus half times 16 times 16 divided by 2. So from here I can write VAB is equal to MAB plus MBA divided by 16 plus 0.5 times 16 over 2. So Now MAB plus MBA. I have these in terms of theta. I can plug here. So VAB will be in terms of theta. For VDC, again, if I look at the free body diagram for column DC, this is MDC, this is MC. This will be column DC, this will be MDC, this will be MCD, this will be shear VDC, this will be shear VCD. Now, if I take moment respect to the C, here I took the moment respect to B, here I will take moment respect to the C. What I will have MDC plus MCD minus VDC times 16 is equal to 0. So from here, if I take the other side, I can write VDC is equal to MDC plus MCD divided by 16. This will be another equation. VDC, if I plug MDC and MCD in terms of theta, so I can find VDC in terms of theta. So I can plug here, if I plug all V, AB and DC here, I can write, let's see, MAB plus MBA divided by 16 plus MCD plus MDC divided by 16. If I take this term to other side, it will be 0.5 times 16 negative 0.5 times 16 divided by 2, that will be equal to 0.5 times 16 divided by 2. So instead of this, I can take the other side, I should put equal to 0.5 times 16 divided by 2. So MAB I have in terms of theta, BABC I will plug in terms of theta, CBCD I will plug in terms of theta, DC I will plug in terms of theta. Here again I have all M in terms of theta. I will have 5 equations, 5 unknown. So I can find from here, I can find theta A, theta B, theta D, theta C and delta. After finding those, I can come back and plug those theta A, theta B, theta C, theta D and delta in slope deflection equations, and I will find these moments. So from there, if you do that, MAB will be equal to 0, MBA will be equal to negative 13.48, MBC will be positive 13.48, MCB negative 77.48, MCD 77.48, and DC will be equal to 0. Okay, thank you so much for watching this lecture. See you next session. Bye bye.